Okay, so now we're going to study Unit 39, an introduction to chemical equilibrium. So many of you may wonder, what is meant by equilibrium? Is it mean balance? Well, they have some similarity, but they have different meanings. So, before we discuss the meaning of equilibrium, let's divide our chemical equation into two parts. The first part is what we call irreversible reaction. Irreversible means they only go into one direction, single way only. There is no U-turn, you cannot go back. There are many typical examples. For example, what about the metal react with acid? All metal eventually will turn into salt and hydrogen in acetic acid. What about neutralization? Yes, the product salt and water cannot go back into acid and base. So very good. If you get enough time, they will have complete reaction in case there is no excess reactant. Yes, so what about in case of excess reactant? That means only product and excess reactant remains. And the reaction will stop. Now here is the key word. The reaction will stop when one or both reactants are used up. So this is what we have learned so far. So what about the second one, reversible reaction? Now, reversible reaction, we have a typical sign, this double arrow. That means the reaction can proceed in both ways. That means reactant can become product, but at the same time, product can turn back into reactant. It sounds weird, right? So let's see. Esterification, the carboxylic acid and alcohol will turn into ester and water, but with hydrolysis, this is something you have learned, right? With hydrolysis, actually, ester can react with water to turn back or break down into carboxylic acid and alcohol. Well, that means some product can turn back into reactant. That's the point. Another famous reaction we will come across in later section is Haber process, the reaction between hydrogen and nitrogen to form ammonia. Yes, both forward and backward reaction proceed at the same time. And no matter how long you provide it, the reaction will never go complete. Well, that means you have no point that one day all carboxylic acid and alcohol will combine to form ester. No, sorry. Because backward reaction always exists. So, as a result, you can expect the reactant and product will exist forever. Both of them can exist. And here is a typical point. So, how can we interpret reaction will never stop, but both reaction and product will exist? Yes, the reaction appears to stop. It looks like stop. So how can we know that? Is with, for example, titration, we can find that the concentration of all species remain unchanged. It looks good, right? Everything's concentration unchanged. It looks like the reaction is stabilized or stopped, but in fact, no. Okay, in fact, no. We call this state is equilibrium. The state that everyone's concentration remain unchanged, we call it equilibrium. But in fact, if we study microscopically, forward reaction and backward reaction never stop. So let's write down this point. reaction rate never equals to 0. And now, here in the chat point, you are asked to distinguish whether the reaction is reversible or irreversible. Now, give you a powerful hint, okay? So you ask yourself, if you get enough time and enough reactants, okay, will the reactant concentration go 0? Yes or no? That is a powerful tool, right? Okay, so you can pause the video and study this first and then continue our video. Now maybe give you 1 minute, okay, if it's enough. Alright, if you forget to pause the video, this is your final chance, okay? And then we go through the answer. First, adding sodium to water. Of course, this is irreversible, right? Eventually, all sodium will turn into soluble salt and hydrogen. Rusting of iron, yes, also irreversible. So if you have enough time, every single iron will turn into rust. Now, we go to part D first. Part D is also irreversible because this is acid react with metal, right? And heating part C, heating iodine crystal in a closed vessel. Now, the key point is closed vessel. There is no way for iodine molecule to escape. So, the crystal will turn into vapor, and some vapor will condense back to crystal. So this is reversible one. No. Okay? And finally, so what about heating the blue copper to sulfate crystal into white and hydrogen one? Okay, right. Let's copy down the equation first. Well, the blue crystal is hydrated one. Alright, after heating, the water of crystallization, now here is water of crystallization, will escape into anhydrous and 5H2O gas, okay? So the gas is escaped. So, but is it reversible? It sounds yes, right? Because they will combine with the molecule of the steam or water molecule in the air to form back into hydrate. It looks like yes, but in fact, no. The point is, there is something missing in our statement. Is closed vessel. So without a closed vessel, the steam here will all escape and gone. After it is gone, there is no point for the anhydrous crystal to capture the steam anymore. So sorry to say, this is a irreversible process. So you can now understand the reaction is important, but the environment is also important, right? A closed vessel is necessary for equilibrium. Oh, no, sorry, for reversible reaction. Right, so please highlight this. Right, so I hope you can handle the checkpoint, right? Well, remember in last page we have come across this one. When everything's concentration remain unchanged, well, then the equilibrium is reached, right? So some of you may wonder, all right, if the reaction stops, okay, in case when the reaction stops, for example, go complete or one of the reactant is used up. So yes, all concentration remain unchanged, right? So can we also say equilibrium is reached? Well, the answer is yes. Okay, equilibrium just mean the concentration of all species remain unchanged. I don't care about how you do it. So here we introduce two terms. The first one is called static equilibrium. Well, static equilibrium is the reaction rate equals to 0. Yes, so you can see two children, their position don't change in the seesaw. No movement. The reaction rate stops. Well, this is typically used in irreversible reaction. So what about the reversible one? The reversible one, we use the term dynamic equilibrium. Well, so let's see this man. This man is trying hard to run forward or towards to left, right? But the machine is moving towards the right. So you can see actually both the man and the machine are moving. They are moving hard, right? But eventually their position, no matter the man or the machine's position, remain unchanged. Well, this is called dynamic because the man runs at the same speed as the machine. So the position remain unchanged. So you can see the typical factor for this one is the reaction rate cannot equals to 0. This is called dynamic. So another typical example for dynamic equilibrium maybe is your money in the pocket, right? So every day you spend money, but every day your parents will give you money back. So eventually you have money in and money out, but the money inside your pocket remain unchanged. This is another interpretation for dynamic equilibrium. Right, so okay, don't worry, this is not so difficult mathematics, okay? Everyone can do it. So let's study this reaction. Well, in the DSE, the equilibrium is mainly about the calculation. Sorry for that, but trust me, the calculation is extremely easy. So let's see. Now, for the first point, so everyone should pay attention, is when in the calculation, what we concern is concentration, not number of mole. So please pay attention. What we concern is concentration. That is involve number of mole and volume. Don't forget volume. Okay? Now, starting time equal to 0. Okay? At the starting, the hydrogen is 0.5, iodine is 0.5. There is no HI, hydrogen iodide. Okay. But at the equilibrium, when everything is settled down, the hydrogen concentration is 0.11, right? Now, here we use the simple mathematics you have learned in mole calculation. Their mole ratio is 1 to 1 to 2, right? So, if 0.5 drop to 0.11, so you ask yourself, how many hydrogen is used up in concentration? 0.5 to 0.11. Yes, drop 0.39. I think easy enough, right? So with the same mole ratio, So what about iodine? First, iodine will increase or decrease? Yes, sure, for decrease, right? Decrease. So what is the concentration decrease? Yes, it's 0.59. I think this is easy enough, right? And with the mole ratio, what about HI? First, increase or decrease? Yes, this is increase. But what is the amount of increase? Yes, don't forget the mole ratio is, right? It's double to what H2 or I2 decrease. That is 0.39 times 2 is 0.78. Now, congratulations, you have finished your job. So finally, this one is 0.11 and this one is 0.78. Not so difficult, right? Yes. So I have mentioned before, in order to start equilibrium, you must have a closed system. Well, otherwise everything is gone. So it's no point for you to have equilibrium. Right. Next one is, well, how can we interpret this experiment graphically? So let's see. With the reactant first, okay? Hydrogen now start at 0.5 and finally at the moment that reach the equilibrium, it turned to 0.11. Okay, what about this way? So yes, it will drop gradually. Eventually, after this point, will become a horizontal line because the concentration no longer have any change. So what about the HI? At the starting, the HI is 0 here, right? But eventually, after the calculation is 0.78. So 0.78, something like here. Alright, sorry. Okay. So it will increase, and then again, after this point, horizontal line. Yes. Now, so you may wonder why both the red line or the blue line are not strict one. Well, it depends on the reaction rate we have come across and in unit 36 and 37. Yes, because take take hydrogen as an example. At the starting, of course, there are plenty of hydrogen, so the reaction rate should be highest. So that's why the slope is the highest. But after time passes with less and less hydrogen, so eventually the reaction rate slow down and the slope is smaller, like this. Alright, this is the first one you should pay attention, this graph. So another one is the reaction rate. Now this is even more serious because this is something new you never learned before. Now, for the forward reaction, as I mentioned, at time equals to 0 or at the starting, there are plenty of hydrogen and iodine, so the reaction rate should be the highest one. So the slope is highest. Right. So with time passes, they will drop. At certain point, they will go horizontal. That means first, the reaction rate will not increase or decrease, but the reaction rate not equals to 0. What about the backward reaction? The backward reaction is the breakdown of hydrogen iodide. Well, at the starting, there is no hydrogen iodide, so of course the reaction rate is 0, right? But with more and more HI, so the reaction rate will increase. At the certain point, at the equilibrium point, they will overlap with the red line. Well, that means both forward ray and backward ray is the same. Forward ray equals to backward ray. And that's why the concentration don't change anymore. Right? So let's study these two graphs seriously, because many students get confused. Okay? Now, and some of you may wonder, the blue line, okay, the blue line is backward reaction. Okay, backward reaction. I am not discussing the way of decomposing HI. Well, there are two different stories, okay? The backward reaction is one. How fast the HI decompose is another story, because the coefficients of HI is 2. So they have two different meanings. So if you have further questions, please ask me, okay? Or PM me. I will discuss more to you. Now, so let's fill in the blanks. Both reactant and product exist in the mixture, and their concentration remain unchanged. And then the next one is the rate of forward reaction equals to the rate of backward reactions. Yes. Now, the importance of reversible reaction is actually the reaction or the equilibrium can start at both sides or either side. It's up to you. At this example, I can show you what about the reaction starts at the product side. Okay, so you can see at time equals to 0, there is no H2 or I2. Everything goes to HI. So at time equals to equilibrium, part of the HI decompose. Now, again, please calculate from 1.0 to 0.78. So what is the amount of HI decompose? It's easy, right? It's 0.21. Oh, sorry, 0.22. Okay, so according to the mole ratio, if that HI is dropped by 0.22, so these two of course increase, right? So what is the amount of increase? Now, be careful with your mole ratio. Okay, with the mole ratio. Yes, this will increase to 111, right? Yes, so again, you have finished your job. So, with this idea, so you can see the equilibrium actually can be reached from either direction. It's okay. The final result still comes to you with the same concentration for every single species. Alright, so let's have a checkpoint again. So try to fill in the checkpoints, please. And okay, let me show you the answer. And here goes. Well, yes, we know that both product and reactant exist in the equilibrium mixture. So how can we interpret? And here comes the term called equilibrium constant. It is actually a ratio between the product and the reactant.